Okay, so here's a couple of power and efficiency questions in the classical mechanics world, just to get a flavour of what we're doing. This is all relatively straightforward, but it's nice to have these things illustrated a bit more clearly. So, say we've got a motor sitting on a table and it's lifting up some load. This load is 15 newtons. The motor's spinning around and it's lifting this thing up. Raising it up in the air. The motor is 3.5 watts. It's lifting this load. It lifts it through a distance of 1.4 meters in 30 seconds. So it takes 30 seconds to do this. So what is the efficiency of the motor? So we want to look at the energy that's gone in, which is going to be, so this is joules per second. Remember, we've got here for watts. So if we've got a 3.5 watt motor running for 30 seconds, then we're going to have 3.5 times 30. That's the joules that's gone in. So 35 times 3, 105 joules has gone in. And that 105, so that's input. Output, what's happened, we've raised 15 newtons through 1.4 meters. So force times distance, 15 times 1.4. So this isn't looking like it's a particularly good motor by the look of it. So 0.4 is 2/5, so we're going to have 621. So that's 21 joules that we've got there. So we put in 105 and we've got 21 out, which isn't great. So the efficiency is the useful stuff that's come out divided by the total amount that's been put in, and that is going to be 1/5 in this case. So we've got 20% efficiency. So that's a fairly simple example of how to deal with efficiency. Let's squeeze in another one on the same sheet here. So if we've got a hydroelectric power station, so we've got 600 megawatts it's producing. We've got water that is starting, so it's starting at the top, it's falling down through the turbines, and then that is producing some kind of electrical output. So it's falling 50 meters before it goes through the turbines. The turbines are 40% efficient. So what is the volume of water that we're going to need every second going through that turbine? So water is 1,000 kilograms per meter cubed. So that makes things a little bit easier. So we've got 600 megawatts coming out rather than writing it at the top. So going in, well, we must have 5/2 of this because we've taken 2/5 of it because our 40% efficiency in order to get 600 megawatts on the way out. So we're going to have to multiply this by 5/2. So we must have there 1,500 megawatts at this point. So every meter cubed of water is going to produce mgh. So that is 50 G. That's our GH multiplied by 1,000. So that is for every meter cubed. We're getting that each meter cubed. So per meter cubed, we're going to be getting this. I'm just going to take G to be 10. It's just easier on this. So that is 1, 2, 3, 4, 5. 5 times 10 to the 5 joules for every meter cubed. We want to get, what is that, 1.5 times 1, 2, 3 times 10 to the 9. So we need to divide one by the other. So let's make that a 0.5 times 10 to the 6, just because it makes it easier to divide. So we've got to have 3,000 meter cubed per second in order to power this hydroelectric station and get the 600 megawatts out. So you're just working through step by step. You can go in order from top to bottom or work backwards. In this case, they've told us the output, so it makes sense to work backwards. Yeah, they might have told us how much water was going through and then work out the efficiency, in which case we're working from both ends and meeting in the middle in order to work out what the efficiency is. Yeah, they could leave any particular bit of it out here. It's like any of these questions, they leave one thing out and you have to work out the other. In this case, they've given us efficiency and output power, and asked us to work out how much water is going in, but they could have asked us for the drop, they could have asked for the efficiency. I mean, there's loads of things they could have asked here. So you just need to piece it together from both directions, work out what's going in, work out what's coming out, and then how those things meet in the middle through the efficiency of the conversion process. So yeah, two fairly straightforward questions just to get a flavour of how power is working in this Newtonian world. We're really going to be coming back to power a lot in electricity. That's probably our main topic, I would have thought, for power alongside classical mechanics. But at least this, gets a flavour of what we're doing at the moment in this particular topic.